Let's solve this second-order linear homogeneous differential equation. We start with y double prime plus 5, y prime plus 3, y prime plus 9, y equals 0. First, let's combine like terms. This simplifies to y double prime plus 5, y prime plus 9, y equals 0. To solve this, we'll use the characteristic equation method. We replace y with r, and each prime reduces the power by 1. So, y double prime becomes r squared, y prime becomes r, and y stays as is. This gives us our characteristic equation. R squared plus 5, r plus 9 equals 0. We can solve this using the quadratic formula. The quadratic formula states that r equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Here, equals 1, b equals 5, and c equals 9. Let's calculate the discriminant first. B squared minus 4, AC equals 25 minus 36, which equals negative 11. Since the discriminant is negative, we'll have complex roots. Now, let's solve for our roots. Plugging into the quadratic formula, we get r equals negative 5 plus, or minus I times the square root of 11, all over 2. This gives us two complex conjugate roots. R1 equals negative 5 over 2 plus I square root of 11 over 2, and R2 equals negative 5 over 2 minus I square root of 11 over 2. For complex roots of the form alpha plus or minus beta I, the general solution takes the form y of t equals e to the alpha t times the quantity c, 1 cosine of beta t plus c2 sine of beta t. In our case, alpha equals negative 5 over 2, and beta equals square root of 11 over 2. Therefore, our final solution is y of t equals e to the negative 5 over 2t times the quantity c, 1 cosine of square root 11 over 2t plus c2 sine of square root 11 over 2t, where c1 and c2 are arbitrary constants determined by initial conditions. This solution represents a damped oscillation, where the e to the negative 5 over 2t term causes the amplitude to decay exponentially, while the trigonometric terms create an oscillating motion.